Sometimes we can be surprised by the performance of an amplifier or other circuit. That might depend on our conceptual models. What do I mean by that? Well, I'm Professor Fiore. Let's dive in and find out. All right, let's get started. We're going to look at a simple two-stage Class A amplifier to illustrate this concept that I'm bringing up. Sometimes circuit performance can surprise you. Let's begin with a basic DC analysis, and then I'm going to look at an AC analysis, and then we're going to get into something a little bit more interesting. First off, I have two stages that are pretty much identical, certainly in terms of their DC bias. So you can see I've got a plus 20 and a minus 10 power supply. The base resistors in both cases, 10Ks. The collector resistors, 10Ks. The loads, 10K. Here it's a 10K in parallel with the Z and base, but that's going to be close enough to 10K. The capacitors are basically the same, 470s here on the emitter. The emitter resistance is a single 10K here, no swamping. And on the second stage, it's a total of 10K for DC, 9.3K plus 700. I realize these are not standard values, but that's not really what I'm going after here. So this is still 10K for DC. It's just that it's going to be swamped in the AC case. So I would expect a higher gain out of the first stage than the second stage. I would probably expect a wider bandwidth out of the second stage than the first stage. Again, because of essentially the feedback that we have here. Probably lower distortion as well compared to this stage. So, we'll start off and look at this DC analysis. Just to cross-check, right? So, first of all, the things that pop up, okay, no surprise out here, 0 volts DC. Oh, a very small, just about negative 65 millivolts sitting on this base. We should get about the same over here. And that's exactly what I'm getting. Might be hard to see that, but that's, again, negative 64.7734, so they're identical. We could check some currents and so forth. Let's see. We're getting about 9.2 volts across this collector resistor, and just about 922 microamps. Over here, we're getting the same exact values. Let's see, the current down here through this emitter resistor is 928.4 roughly. Same thing over here, 928.4. All right, the voltages here are different because this is split, right? I've got the 9.3 plus 700 versus a single 10K. So basically, the DC looks fine, right? Do remember this negative 65 millivolts sitting on the base. We're going to use that down the road. It's small. Just remember that it's about 1/10 of what we'd expect the base emitter potential to be. All right. All right. Now let's go and do a real quick Bode plot on this thing. We'll see what we can get as far as a nice gain plot. All righty. So let's see. Where's our legend? So the gain, let's see, V out stage 1 is the green. We can see that's somewhat over 40 dB, pretty big. The V out number 2, that's sitting up here about 60. So we're getting, upper teens for the gain on the second stage in dB, right, versus 40. So that works, generally speaking, what we would expect, right? We expect this because it's not swamped, to have a higher gain than this. The frequency response looks like it's largely dictated probably by the first stage. We can see the roll-offs at the output of the second stage are pretty much the same as the first stage. And this is a nice wide bandwidth. We can say, clearly 100 hertz up to, a few hundred kilohertz. This thing is nice and flat. The phase response, we're looking at on the first stage, we're looking at minus 180 degrees. It's inverting, which we would expect. The second stage is also inverting, but we invert the inversion, so we're back to 0 degrees for that. So so far, nothing out of the ordinary. You know, granted, I'm not drilling down into this in terms of exact gains and so forth, but in the coarse look at things, right, back of the envelope kind of calculations, this stuff looks fine. What's so surprising? Well, there is something else we can do here, right? We can, in fact, maybe look at a transient analysis. All right, let's separate these curves out so we can see them. So the Vn, nice sine wave, right? I dialed that in for a 1 kilohertz, 5 millivolt peak sine. So that looks beautiful. V out number 1, you know, as we said, there was going to be a pretty high gain there over 40 dB, which would be a voltage gain of 100 in ordinary form. So we're seeing a bit more than that, right? Because this is, you know, 800 up here. So, you know, that's looking somewhere around maybe like 600 or so. So we're getting a little bit over 100. It's also inverted. That looks good, you know, verifying the phase. Then we've got a further gain, which we said was a little less than 20 dB, 20 dB being a gain of 10. So, all right, that looks sensible. You know, this would be, you know, maybe a gain of you know, 15 upper teens anyway, right? So we're going from, you know, 600, 700, whatever it works out to millivolts over here, a little under 5 volts there. It's inverted again, right? So it invert the inversion, and we have this signal that looks nice compared to my input. You know, and they're not even really all that bad looking sine waves, okay? Everything seems to be fine. But let's dive in a little closer. And what I want to do in this case is look at the distortion. So you would expect, right, the first stage, because it's not swamped, would have more distortion than our second stage, because that's swamped. All right? So let's just do a little Fourier analysis and see what we come up with for V out number 1. So I can do a little shortcut over here with my little pop-up menu, Fourier series, set that up 1K. All right, 16 points will be enough. And let me open this up a little bit so we can see it. All right, so the total harmonic distortion is a little over 3% here. You know, when you're only talking about 1, 2, 3, 4%, it's really hard to see that with the naked eye unless you have a very sort of trained eye here and you can really zoom into the waveform and look at it. You know, you got a sine wave with a couple percent distortion. It's going to look superficially pretty good when you do a time domain plot like this. But we can get some idea of what's going on with the harmonics, right? What's going on inside there. So we see the fundamental is sitting at about 690 millivolts. So that agrees with what we're seeing over here. And really, there's only one big strong harmonic, and that's the second harmonic, right? That's 690 for that. This is about 21, just shy of 21 millivolts for the second harmonic. And that by itself, you know, about 21 compared to nearly 700, you know, that's about 3% right there, which is our total harmonic distortion. Everything else is considerably less than a millivolt, right? I mean, the third harmonic is sitting at about 300 microvolts. The fourth is about 155-ish microvolts. And then it's like 19, 20, 15, 9, 15. You know, these are really small. So we can see, yeah, okay, it's pretty much all second harmonic, which by itself shouldn't be too surprising because after all, it's a Class A amplifier. You know, a Class A style amplifier produces even harmonic distortion. So that by itself, unsurprising. Now let's go over and look at V out number 2. Now remember, we've got basically 3% THD in stage 1. Now I'm going to look at V out number 2. I'm going to do the same thing. Fourier series for that. Same specs. Let's do a calculation. Obviously, the first thing I'm going to say is, you know, our fundamental is a lot higher, obviously, because of the gains, about 4.5 volts. But let's open this up. Notice the total harmonic distortion is only 1.6%. It's 1.59 and change. That should get your attention. That should get your attention. Remember, what we're looking at right here is V out number 2. In other words, this output right here on this collector. This is not the distortion of the second stage. We expect the second stage to have less distortion than the first stage because it's a swamped amplifier. But that's not what we're talking about here. What we're talking about is the distortion through the entire system. A distorted signal, V out 1, is coming into the transistor number 2, and that has no way of knowing, right? That has no way of knowing that some of this is distortion. It's just supposed to amplify whatever's coming in. And obviously give it a little bit of its own distortion, right? And that's what comes out here. So we are not saying that the distortion of stage 2 is 1.59%. We're saying that distortion of the entire amplifier is 1.59%. Just think about that for a sec. And while you're thinking about that, I want to run through some of these numbers. Now remember, in the preceding case, for V out number 1, virtually all the distortion was second harmonic, and that was about 3% of the input signal, and our THD was about 3%. Everything else was really tiny. Here, compared to that, we see that the second harmonic is suppressed. It's only 34 millivolts compared to about 4.5 volts. So it's less than 1%. And then the third harmonic is actually a little bit bigger. It's 55 millivolts. Then we get about, just about 28 millivolts for the fourth harmonic. And then, they start dropping down, right? So clearly we've got a bunch of things. The sort of fingerprint, the signature of the distortion is different in this amplifier. And the really noticeable thing I would say is, well, there's this jump in the third and fourth harmonic, but there's a sizable reduction in the second harmonic, which was the major contributing factor to the distortion in the first stage. Now, let's back up just a sec. We're saying from the input to V out number 1, there's a 3% THD. We continue that through the stage 2. V out number 2 is sitting at just about half of that, 1.59% THD. So how is it that I can get less distortion out of this thing than I have coming into it? Doesn't that seem a little weird? Doesn't that seem a little unexpected? Like, even if this amplifier was zero distortion, right? Let's say it was like super hi-fi 0.00000000001% THD, you'd say, okay, well, whatever I have coming in here, 3%, that's what I would have coming out, 3%. If this thing is going to produce distortion, then it's going to distort my input signal plus the added distortion. I expect more distortion. How could I possibly wind up with less distortion? Now, we already know, right? We already know that this is not a matter of frequency tailoring. It's not like these higher harmonics are being artificially reduced. We already looked at the bandwidth of this thing, and it went out to several hundred kilohertz. I'm only testing this with 1 kilohertz. So, it's flat, way, way, way above what we're actually looking at as far as distortion harmonics. So that's not the issue. How is it that V out, and I'm going to tell you right now, stage 2 is not distortion free. It does produce its own distortion, and we could actually build this up and figure out what the distortion on this, and I'll tell you right now, if you put a 5 millivolt sine wave into it at 1 kilohertz, what you will get out of here will be less than the 3% that we're getting out of the first stage. I'll guarantee that. We do have a larger signal coming in here though, right? So maybe you would say, well, it's a bigger input signal. I will get some more distortion. Yeah, sure, definitely. But we're still left with this little quandary. How the heck is V out less distorted than this V out over here? The input has more distortion in the output. Well, this goes back to this idea of the mental model that I was talking about, right? What's your conceptual framework for this? In other words, we know how individual transistors work, but we also have I don't want to call it emotional baggage, but we have kind of a sort of intellectual / emotional baggage that's attached to things like this. You know, we have these sort of large conceptual, you know, overarching kind of ideas about things. And one of them, when it comes to distortion, is that, you know, distortion is bad. We don't like distortion. If we're looking for high fidelity, distortion is evil. Granted, there are times when we like distortion, you know, fuzz guitar, for example, but in an audio amplifier, unless it's being used for some kind of artistic expression, if we're just trying to reproduce something faithfully, distortion is an enemy. We don't like distortion. So, if you think of it like dirt, think of distortion like dirt. I mean, people sort of, right, you don't like dirt. Nobody really likes dirt. I mean, okay, you know, we like dirt as far as growing crops, but as far as like things being dirty, right, the concept of being unclean, that's undesirable, right? The more dirt you have, the worse the situation is. So, you know, you're a kid, maybe you're an adult, you got a cookie, you drop the cookie on the ground, it's dirty, right? Now you might just say, you know, well, I don't care if it's dirty, it's a cookie, it's a cookie. I'm going to have the cookie. But, you know, a parent or a friend or, you know, somebody, right, might say, hey, you dropped the cookie on the ground, it's dirty. You would never consider rubbing more dirt on the cookie to make it clean, right? That's like crazy. You would not do that. So it's the same kind of thing that we see with a signal being distorted. It's distorted. You're not going to make it less distorted by adding more distortion. That's the sort of conceptual model that people have. In other words, the idea is, well, you put the signal in, the first stage degrades it, it distorts it. That goes into another stage that has its own level of degradation. And this just continues stage after stage after stage, and things get a little worse and a little worse and a little worse. And the idea is, of course, you want the whole system to be as clean as possible, and therefore each individual stage to be as clean as possible so that you can get the nicest result. And I will tell you right up front, if you're going to design a hi-fi amplifier, you in fact try to get every single little generator of distortion, every single little item there, you want to mitigate its effect on the output. That's the way you design a good amplifier, right? Try to get everything as distortion-free as possible. Here's the rub. This whole dirt idea that we buy into, that's not really how distortion works. Distortion is basically caused by nonlinearities in the system. In other words, the input-output plot, right? If you were to draw a little graph, you know, the input on the x-axis and the output on the y-axis, a perfectly linear amplifier would just be a straight line, you know, coming up at some angle. Nonlinearity basically means that line is not straight. It's not perfectly straight. There's some kinks in it. There's some bends, some changes in that. And when you pass a signal into it, it bends, so to speak, the output wave. And, you know, we call that distortion, right? If you distort something, if you sort of bend it in the time domain, you also alter it in the frequency domain. And we know that if you distort a signal, you add harmonics, right? That's what we were looking at just a moment ago. But here's the really cool thing. If you know what those nonlinearities are, right? If you have a good mathematical model for them, if you know where they're coming from, it might be possible to apply those nonlinearities in reverse. And if you do it right, that can partially cancel. In other words, you can think of it as unbending the bent wave back to something that's closer to what you originally started with. And then the end result is the amplifier has less distortion at its final output than it does partway through, which is exactly what we saw. So let's take a look at that. Like how does that circuit, that little two-stage amplifier, sort of unbend, if you will, the waveform in the second stage. But before we do that, I do want to, say this again, second time. If you want to make a low distortion amplifier, try to get rid of every distortion producing mechanism in there. You don't try to use some trick later on to correct for distortion. As I always told my students, an ounce of prevention is worth a pound of cure. Or even better, a gram of prevention is worth a kilo of cure. Better to take that little time up front and get rid of a problem before the problem occurs than trying to go in now that you have this fully manifest problem and deal with it then, right? Deal with it before it's even a problem. All right, so back to our circuit. And by the way, please do not take this as some great hi-fi amplifier. It is not. This is here to just illustrate this point that I'm trying to make. So the first thing I'm going to do here is, I mentioned sort of offhand Class A amplifier, and it's going to produce even harmonics, right? So if you've looked at this in a simulator or in a lab, if you crank this input signal up a little bit, I'm going to force this thing to a place where it's going to start distorting, obviously, to your eye. I'm going to double the input, 10 millivolts, right? 10 millivolts peak. And this will be big enough to make the output clip. But I don't really care about Vout2. I really want to focus in on Vout number 1. So we're going to do a little transient analysis over here. Alrighty, now let's separate these out. And probably don't need this, but I'll put it in. So Vout1 is the green, Vout2 is the output, which clearly now is obviously clipped, right? Don't care. I really want to look at Vout number 1. What might not be immediately apparent is this thing is asymmetrical. It is distorted. Now we can, let's see, I'm going to get rid of that waveform so it's a little bit bigger and then kind of spread it out here a little bit. Matter of fact, I could zoom in here. This got a couple of waves and we can see that. All right, now look carefully at the top half of this sine wave versus the bottom half, and do likewise on the input sine wave, right? So this is, mathematically a nice pure sine wave. What do you see? Well, when I look at this, I immediately notice this positive peak is kind of fat and broadened compared to what I'm seeing over here. Or better, compared to what I'm seeing down here, right? So this is sort of fat, squished down, and by comparison, this is kind of elongated, right? Look at how sharp this peak is compared to this sort of, like I said, sort of fattened kind of peak. Now, you might say, well, is this just like a DC offset? Because, this is +2 and this is -2. And look at this distance to this peak and this distance to this peak. They're not the same. No, they're not. It's because they're distorted. It's not because there's a DC offset. Remember, we had a DC offset on the base over here, which is what we're looking at right now, it was just under 70 millivolts. It was like 64, 65 millivolts, something like that. Now, what am I getting on my peaks? So on this peak, I'm getting like 1.19, almost 1.2 volts. And on the negative peak, we're getting a negative about 1.57, 1.58. Well, even if you tack on another 70 millivolts, right? Or in this case, you'd have to subtract off the 70 millivolts, in which case you'd be about 1.5. And up here, you'd add it on, right? And you'd be, you still wouldn't even be at 1.3. So it's this shifting, what looks like shifting, is not just a DC shift. It really is because the waveform itself is distorted. All right? And that's because, since we don't have any swamping, right, the transconductance curve starts out low, right, and pops up like this. You get a steeper and steeper slope. We know that as the current goes up in the emitter, our prime E gets smaller. And as R prime E gets smaller, the gain goes up. So as the input signal comes in, that instantaneous current is going up and down, and different parts of that sine wave that are coming in are getting different gains. So when the signal is big, right, like this, there's a lot of current, which means you get a lot of gain. But that corresponds to this because, of course, this is an inverting amplifier. On the other hand, when it's at the other extreme, small signal, that's small current, that's a big R prime E, meaning we get a small gain. And that's what's happening here. We're not getting enough gain. The gain, if the gain was consistent, this thing would come up and it would be up here somewhere and then come back down. Likewise, down here, it wouldn't reach this peak. It would follow like this, and then it would kind of come in like this. All right, so this would kind of end like this, and then this would be coming up to a bigger peak, right? That's because of the R prime E change. All right, so what does this have to do with stage 2? Well, stage 2 is also a Class A amplifier. It's going to do the same kind of thing, okay? So I'm going to get back to the original waveform here, original amplitude. And we'll do another transient analysis. So I can look at all of the waveforms. All right, input signal. Inverted, and like we said, you don't see it as well here, but this is sort of flattened, and this is sort of peaked. Now you feed that into the second stage. So here's the part that was flattened, and it is the big signal, like this was, right? This is the big signal. And what happened with the big signal? It got extra pointy. It was the small signal that got flattened, right? There's the, and inverted, but that was the signal that got flattened. So now the same thing kind of happens in mirror image, right? So here's the part that was kind of pointy, and it's now, because it's small, because it's, the low amplitude version, right? It's negative 800 millivolts rather than like positive 800 millivolts. That is going to get the small gain. That's going to wind up getting kind of squished, which is this peak right here. Meanwhile, the fattened peak up here, that's the big gain, right? So that's going to get kind of pointy and flipped upside down. So you're going to take the squished part and make it more pointy. You're going to boost it up. And then the pointy one, you're going to kind of squish. And they kind of cancel out. Not perfectly, right? I mean, there's other distortion in here, but that's why the second harmonic, because that's like, the second harmonic is like the biggie when it comes to creating this kind of distortion in this waveform. That's why the second harmonic is so small, comparatively speaking, right? I mean, it was like 3% for the second harmonic in V out number 1, right, for this stage. And it was less than 1% in V out number 2. Because V out number 2 is producing this mirror image. It's unbending the bent wave. The part that was pointy gets squished, and the part that was squished gets pointy. So, if you could do it perfectly, what would come out of the second stage would be distortion free. And here we are, basically rubbing dirt on a cookie to make it clean. Right? So, if that's your conceptual model, your mental model, that, it's degradation and it's just going to get worse and worse and worse and worse and worse. Well, not really, right? You have to think of this in like mathematical terms. I know like some people don't want to do that. They're maybe afraid of the math or they want to run away from the math, but it's really important if you really want to understand what's going on here, because now you could use that idea. You can use that concept in other places. You can compensate for things. You can pre-distort waveforms to get a different kind of output that you're looking for, right? That's a very powerful concept. It's something that we look at in the op amps book and the list of videos for that in an area called function synthesis. That's a very useful concept. So just keep this in the back of your mind, right? This is caused by a nonlinearity. If you know what the nonlinearity is, and you can make a mirror image of it, then you can compensate in part, or hopefully in whole, and get something nicer at the output. Cool. Well, I hope you enjoyed this and learned something from it. And until next time, this is Professor Fiore saying, take care, have a good one.